Has it ever crossed your mind how the entire cosmos is in rotation, and simultaneously we perceive ourselves as perfectly motionless? The planet Earth rotates at more than 1,000 miles per hour, orbiting the Sun from 93 million miles away, while the whole solar system itself speeds through our galaxy at almost 500,000 miles an hour. And even so, we perceive absolutely nothing. Our pulse does not quiver. Our breathing doesn't waver, as though we are held immobile within a cosmos that is perpetually moving. But consider this. What if that very motionlessness is the most profound illusion of all time? What if time as we know it is merely the resonance of a much deeper spin? A rotation that started before atoms, preceding light, predating memory. Tonight we venture into that enigma to explore not just why elements move, but why nothing is capable of halting its movement. So please, close your eyes. Allow the vibration of the cosmos to hum beneath your skin, and journey with me into the swirling core of existence. Before we commence, if you are feeling generous, a simple like or a gentle tap on the subscribe button would be invaluable to me. It is a minor gesture, but I receive it with profound appreciation because every piece of your encouragement helps this minuscule universe stay vibrant and reassures me that these hushed narratives continue to find their home in gentle hearts just like yours. Now, let's commence with the initial query. Part 1. If all things in the cosmos are whirling, why do we feel stationary in time? The Earth is rotating at over 1,000 miles per hour, spinning consistently right under your feet. At this very moment, it is also hurtling around the Sun at nearly 67,000 miles per hour. And as you are breathing this second, the complete solar system navigates around the Milky Way at close to 490,000 miles per hour. Yet, remarkably, we do not register any of it. The coffee resting in your mug shows no ripples. The atmosphere does not create drag. The stars look static. This is one of the premier illusions of our reality, a contradiction of kinesis and tranquility. From the tiniest electron to the most massive cluster of galaxies, everything in the cosmos spins. Atoms revolve, planets orbit, galaxies contort in immense spirals of illumination and dust. Even the universe in its entirety, as per some cosmological theories, might possess a faint global rotation inscribed into its fundamental structure. But why, if all is in perpetual motion, do we feel so utterly still? The explanation starts with inertia, one of the quietest yet most dominant principles in all of physics. Isaac Newton initially articulated it in the 17th century. An object in motion perseveres in motion unless influenced upon by an external force. This statute is the clandestine reason we cannot sense the planet's unceasing rotation. We are traveling with the Earth, not in opposition to it. Your physical form, the air surrounding you, the oceans, the mountains, all of it rotates in unison, secured in a singular, silent cadence. To perceive movement, you require a differential, a nudge, a pull, a modification. But no such modification exists here. The Earth's rotation is unwavering, fluid, and primordial. It remains the same today as it was when the first humans gazed up at the constellations. Astronauts, similarly, witness this illusion on an even grander scale. While in orbit, they move at 17,500 miles per hour, encircling the planet every 90 minutes. However, inside their spacecraft, everything seems tranquil. Without resistance, lacking atmospheric friction, motion registers as stillness. This occurrence is known by a name: uniform motion. It is the very principle that permits you to sip tea on an airplane cruising at 500 miles per hour. You and the aircraft are moving as one. Only when turbulence, an abrupt change, disrupts that uniformity. Do you actually sense the movement? The Earth's motion, too, is flawless. No tremors, no friction, no sudden alterations. And because space is nearly a flawless vacuum, nothing exists to signal to us that we are revolving at cosmic velocities. Neil deGrasse Tyson remarked, "We are on a space rock that is orbiting a star that is orbiting a galaxy that is moving through the universe, and we call it home." It is simple to overlook because our senses were not designed for such proportions. Our inner ears, which register motion and equilibrium, adapted to manage walking, running, or ascending, not the rotation of a planet thousands of miles in diameter. They react to acceleration, not to consistent velocity. This is why you sense the start of a car, but not its steady cruise. On Earth, everything is moving along with you. There is no initiation or cessation, only an everlasting glide. Nonetheless, scientists are able to measure this concealed motion with astounding precision. The Foucault pendulum, first displayed in 1851 by Léon Foucault, swings independently back and forth while the ground beneath it incrementally turns. It requires no stars to validate Earth's rotation. Its gradual twist over many hours is the Earth's spin rendered visible in silence. If you have ever stood beside one of these pendulums in a museum, you have witnessed time and motion coalesce, one gentle arc at a time. On a cosmic level, this rotation is far from inconsequential. The Earth's spin establishes day and night, stabilizes the planet's magnetic shield, and safeguards us from solar radiation. Lacking it, our world would be incinerated on one side and perpetually frozen on the other. NASA's Goddard Space Flight Center observes that the planet's rotation has been decelerating fractionally over billions of years, primarily due to the Moon's tidal influence, adding roughly 1.7 milliseconds to the duration of each century's day. So even within our perceived stillness, there is transformation. Slow, imperceptible, but tangible. When we examine more closely, rotation is not just an earthly event. It is a cosmic hallmark. Stars materialize from collapsing clouds of gas and dust, and as they condense, they spin more rapidly. This is the conservation of angular momentum, the very same principle that allows a figure skater to accelerate her spin when retracting her arms. Every planet receives this momentum. The Earth's 24-hour rotation is a fossilized remnant of that primeval vortex of creation. Even the Sun rotates once every 27 days, dragging its magnetic field across space like incandescent threads. And the Milky Way, our galactic residence, completes one turn every 230 million years, transporting hundreds of billions of stars in a spiral choreography that started long before our planet came to be. The James Webb Space Telescope, JWST, has imaged galaxies so remote that their light has journeyed for over 13 billion years. And even those primordial galaxies display indications of rotation. ESA scientists analyzing these early structures discovered subtle variations in light. One side marginally red-shifted, the other blue-shifted, an unmistakable signature of spin. It appears that the propensity to rotate is inscribed into the universe's very DNA. But how can everything be revolving and yet seem so perfectly still? A portion of the explanation is found in relativity. As Einstein proposed, there is no absolute motion, only motion in relation to something else. Thus, from our viewpoint on Earth, we are at rest, and it is the cosmos that revolves. From a different framework, the reverse is accurate. This symmetry is what maintains the consistency of physics and what renders our stillness an illusion of viewpoint. In the depths of space, astronauts aboard the International Space Station orbit Earth at nearly 5 miles per second. but they encounter weightlessness, not motion. Their perception of down shifts every 90 minutes, yet their consciousness adapts. We, too, are passengers in transit, acclimated to the calm. Our stillness is a mechanism for survival, an equilibrium between what our senses can process and what the cosmos necessitates. If we could somehow register the motion of the Earth, the pull of the sun, the drift of the galaxy, our very perception of time itself would disintegrate. Because motion and time are inextricably linked. Just as rotation defines our days and years, it also establishes the heartbeat of the cosmos. Time, as Carl Sagan once articulated, is woven into the very structure of the universe. And we are the fiber. The tranquility you experience now is not the negation of motion. It is the symphony of everything moving in unison. So when you rest tonight beneath the invisible revolution of the stars, recall this: you are not standing motionless. You are drifting through a cosmic current, gently, perpetually, unendingly. Each moment of stillness is merely the universe moving too fluidly for you to perceive. And in that flawless equilibrium of motion and serenity, life discovers its quiet cadence. Take a deep breath. You are revolving. You always have been. And the silence you perceive is the sound of everything moving as one. Now, as we float deeper into this narrative, let's gaze backward to the instant before movement initiated, when the universe itself executed its first turn. That is where our subsequent chapter starts. Part 2. Who initiated the universe's spin? If you could rewind time, not by centuries, not millennia, but all the way back to the very first second following the Big Bang, what would you witness? Would there be illumination? Would there be sound? Or would there exist only an abrupt motion, a swirl, a torsion, the absolute first rotation of everything that would ever come to be? The query of who or what imparted the universe with its initial spin is not a question of philosophy, but rather of physics. It rests concealed deep within the equations of cosmology, inside the most nascent moments of time when matter, energy, and space itself started to materialize. Astronomers refer to this as the Planck era, a window of time so early, within 10 to the power of negative 43 seconds of the Big Bang, that our contemporary laws of physics cannot completely fathom it. But the little we can deduce hints at something phenomenal. The universe might have been born not in quietude, but in a gentle rotation. Today, scientists analyzing the cosmic microwave background, the residual afterglow of the Big Bang identified by satellites like WMAP and Planck, ESA, have discovered minute irregularities, small ripples in temperature only a few millionths of a degree in variance. These patterns indicate that the nascent universe was not perfectly homogeneous. There were subtle distinctions, and those distinctions evolved into everything we observe today: galaxies, stars, planets, and life itself. But some researchers observed something more peculiar: a faint alignment, a sort of large-scale torsion in the arrangement of those ripples. They dubbed it the axis of evil, a baffling pattern implying that the universe on the grandest scales might possess a favored direction of rotation. According to NASA's WMAP mission data and subsequent observations by ESA's Planck satellite, this alignment could signify one of two possibilities: either a subtle anomaly of measurement or tangible proof that the entire universe once rotated. If correct, that spin could have influenced everything from the spiral structures of galaxies to the very arrow of time. How could such a rotation even start? The solution may be found in quantum fluctuations, minuscule, random variations in energy that transpired when the universe was smaller than an atom. Even in absolute emptiness, these fluctuations occur spontaneously. As NASA's Goddard Space Flight Center details, quantum fields are never perfectly static. They jitter. When the Big Bang occurred, those jitters were elongated and magnified by cosmic inflation, a brief yet staggering expansion that caused the universe to swell faster than the speed of light. That swift stretching might have converted some of those quantum jitters into swirling motions. The first cosmic spins. Inflation theory, formulated by physicist Alan Guth in 1981, clarifies why the universe seems so uniform and homogeneous, yet simultaneously contains the foundations of structure. But in more recent years, data from Planck and BICEP-2 experiments hinted that during inflation, subtle rotational modes, designated as B modes, may have permeated the primordial gravitational waves. These tiny curls in spacetime could be the fossilized evidence of the universe's inaugural rotation. They suggest that the Big Bang was not merely an outward burst, but a twisting genesis, one that impressed spin across every magnitude of matter. And this is logical when we observe what transpired next. As the universe expanded and cooled, matter started to coalesce. First quarks and gluons, then protons and neutrons, then atoms. Each possessed tiny measures of angular momentum. When gravity subsequently gathered them into clouds and galaxies, that primordial angular momentum was preserved. It is the identical principle that causes a figure skater to spin faster by retracting her arms. In physics, nothing spins from a void. Motion must originate from motion. And thus the first spin, regardless of its size, had to be present from the very start. Astronomers today can observe the imprints of that rotation in remote galaxies. In 2011, researchers from the Harvard-Smithsonian Center for Astrophysics studied over 15,000 spiral galaxies and discovered a subtle inclination in their rotation direction, an asymmetry that might trace back to the early universe's spin. While not yet definitive, this handedness of the cosmos implies that our universe may not be entirely stochastic after all. There might be a concealed rhythm, a silent turn that all things still adhere to. Even dark matter, that imperceptible scaffolding that binds galaxies, could possess a spin signature. Computer simulations by NASA's Jet Propulsion Laboratory illustrate that dark matter halos contort and revolve over billions of years, steering the visible galaxies within them much like whirlpools steering leaves. Without that rotation, galaxies would disintegrate. It is as if the nascent universe set everything revolving. And even today, the resonances of that motion maintain the stars in equilibrium. Still, the origin query persists. Who or what initiated the spin? Physicists rely on one quiet explanation: symmetry breaking. In the earliest fractions of a second, the forces we now recognize as gravity, electromagnetism, and the nuclear forces were momentarily united. But as the universe cooled, they started to diverge. When that symmetry fractured, tiny asymmetries, tiny flaws, materialized. Those flaws, according to the European Space Agency, are what permitted structure, motion, and spin to arise. In a perfectly balanced universe, nothing could ever move. But a slightly unbalanced one? It could dance. We can observe this principle mirrored everywhere, in the direction galaxies revolve, in the manner atoms rotate, even in the way neutrinos exhibit a left-handed preference. Nature, it appears, is not perfectly symmetrical, and that minute imperfection is what permits everything to turn. Some scientists have even attempted to ascertain whether the entire universe is rotating. In 2020, astrophysicist Lior Shamir from Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. he discovered that galaxies in one half of the sky tend to revolve more in one direction than the other, indicating a large-scale cosmic spin. As Shamir documented, the universe may have a collective pattern of motion, a preferred direction that began in the early universe. This does not imply the cosmos is spinning like a child's top. Rather, it might signify that the structure of spacetime itself once twisted fractionally during its expansion. Even a subtle torsion could cascade across billions of light years. To us, it feels imperceptible, but on a universal scale, it could define the geometry of everything. To verify these theories, NASA and ESA persist in mapping the universe in ever-increasing detail. The James Webb Space Telescope is already documenting the light of galaxies that materialized just 300 million years after the Big Bang. Some of these ancient systems already display organized rotation, spiral patterns far too early in cosmic history to be accounted for by chance. That signifies the seeds of spin were sown almost instantly. The universe did not need to learn to rotate. It was born already turning. Even on the quantum scale, spin is elemental. Every particle, electrons, protons, neutrons, possesses intrinsic spin, a built-in characteristic of matter articulated by quantum mechanics. It is not the kind of revolution we picture physically, but a more profound mathematical rotation encoded in the wave function itself. As physicist Richard Feynman once noted, spin is one of the most profound properties of nature. It is not that the particle is literally spinning. It simply has spin as it has mass. So, in one respect, rotation was not introduced later. It was integral to the blueprint of existence. When you observe the night sky, you are witnessing the inheritance of that motion. Every galaxy's swirl, every planet's orbit, every photon of light, all originate from that first cosmic rotation. Without it, matter would never have aggregated, stars would never have ignited, and time itself would possess no rhythm. Motion is not an anomaly of the universe. It is its pulse. And though we might never ascertain exactly what initiated that first spin, the evidence persistently whispers that it has always existed. Quiet, steady, imperceptible, yet inscribed into everything we can observe. As an ESA cosmologist, Jan Tauber, once remarked, "The universe carries memory, not in words, but in patterns of light." And within those patterns resides the faint signature of the first motion, a torsion more ancient than time itself. So when we inquire who set the universe spinning, the most truthful answer may be that the universe never learned how to move. It was born already in motion. The spin was not fabricated. It was inherited. Take a breath. The atoms in your body, too, are still revolving with that initial impulse. From the smallest electron to the swirl of the Milky Way, the identical rotation persists, uninterrupted for nearly 13.8 billion years. We are not distinct from that motion. We are its continuation. And as we progress onward through this narrative, we encounter the next query, one that emerges organically from the last. If rotation defined the birth of the universe, could it also be the explanation for why life itself exists? That is where we venture next. Part 3. Did spinning enable life? Without rotation, Earth would be muted. No day, no night, no climate. Only a frozen hemisphere and a scorched one. A dead planet, adrift in illumination. But because it revolves, this planet respires. Every dawn, every ocean wave, every gust of wind, they all originate from the same ancient turn that commenced 4.5 billion years ago. The Earth's spin is not merely a motion, it is a generator, a delicate equilibrium that underpins everything we recognize as life. From the magnetic shield that guards us from cosmic radiation to the cycles of temperature that foster oceans and clouds, rotation defines our world in ways both apparent and imperceptible. According to NASA's Goddard Space Flight Center, our planet's rotational velocity near the equator is about 1,037 miles per hour, finalizing one full spin every 23 hours, 56 minutes, and 4 seconds, what scientists term a sidereal day. This unwavering rhythm dictates the tempo for all biological and environmental cycles on Earth. Every plant, animal, and ocean current is synchronized to it, an invisible metronome pulsing beneath everything animate. The primary consequence of Earth's rotation is the fluctuation of day and night. It allocates sunlight across the surface, fashioning temperature gradients that propel wind, currents, and climate. Lacking that daily rotation, one hemisphere would incinerate under perpetual daylight, while the other solidified in eternal blackness. The borderline between them would be a ferocious barrier of storms, a lifeless crepuscular zone. But because Earth revolves, the sun ascends and descends, and energy is distributed evenly enough to permit stable climates and habitable territories. Rotation also influences Earth's magnetic field, one of the most vital shields for life. Deep below our feet, the planet's liquid iron core shifts and churns, activating a magnetic dynamo. As NASA's magnetospheric multiscale mission portrays it, the Earth's magnetic field is produced by the movement of molten iron within its core. This field repels the solar wind, a current of charged particles continuously discharged by the sun. Without it, those particles would erode away our atmosphere, much like the events on Mars. The red planet rotates once every 24.6 hours, nearly identical to Earth. But its smaller, cooled core ceased its molten motion eons ago. Without an operational magnetic field, its air was gradually worn away by the sun's radiation, leaving a barren, frozen wasteland. Here on Earth, the magnetic field also sculpts the auroras, those ethereal, glowing curtains of light near the poles. They are not just phenomena of beauty, they are proof of safeguarding. Where magnetic lines flex and engage with charged solar particles, light is generated, a reminder that our planet's rotation still fuels an invisible force field surrounding us. But the spin's impact does not cease at shielding and sunlight. It also directs the atmosphere itself. Because Earth turns, air journeying from the equator toward the poles deviates, a phenomenon recognized as the Coriolis effect. This effect generates the immense spiraling systems of winds and currents that characterize our weather. It is why hurricanes revolve, why jet streams flow, and why ocean gyres transport warm and cold water across the planet. Without the Coriolis effect, weather systems would devolve into disarray, storms would not materialize, and climates would not find balance. In truth, the rotational velocity of a planet directly defines its climate. NASA's Global Modeling and Assimilation Office, GMAO, has modeled exoplanets with slower or faster spins. A decelerated rotation forces one side to overheat and the other to freeze, while a more rapid one can generate ferocious winds and briefer days that imbalance atmospheric stability. Earth's 24-hour cadence is almost flawless, lengthy enough to allocate energy uniformly, but brief enough to avert overheating. The duration of a day also impacts biology. Living organisms evolved internal clocks, circadian rhythms, that align with the planet's rotation. According to research disseminated by the National Center for Biotechnology Information, NCBI, every living cell on Earth possesses a molecular timekeeper that syncs to this 24-hour cycle. This rhythm manages when plants unfurl their leaves, when birds commence migration, and even when humans experience sleep. If the Earth ceased its rotation, this biological synchronization would fracture. Light and dark would no longer fluctuate predictably, and life as we understand it could not acclimatize. Rotation also influenced how the Moon became our celestial partner. Billions of years ago, a Mars-sized body named Theia collided with the nascent Earth. The impact propelled debris into orbit, which subsequently coalesced into the Moon. The collision also accelerated Earth's spin significantly. Over eons, the Moon's gravity has been decelerating that spin, progressively extending our days from roughly 6 hours to the 24-hour cycle we experience now. Tidal interactions between the two bodies maintain the planet's axial tilt stability, averting drastic climate fluctuations. The Gaia mission corroborates that this stability is paramount for long-term habitability. Planets that oscillate too erratically often endure catastrophic climate shifts. The Moon and Earth now persist in a slow gravitational symbiosis. The identical tides that sculpt our oceans also decelerate our rotation by approximately 1.7 milliseconds per century, as documented by NASA's Jet Propulsion Laboratory. It serves as a reminder that even the duration of our day, the pulse of our world, is progressively altering, one imperceptible moment at a time. If we gaze beyond our own planet, we discover that rotation assumes a comparable role in other worlds. Jupiter, as an example, revolves once every 9 hours and 56 minutes, positioning it as the fastest rotating planet in the solar system. Its velocity fuels ferocious jet streams and tempests, including the Great Red Spot, a hurricane larger than Earth that has persisted for centuries. Rotation there generates chaos, yet concurrently stability, allocating heat and sculpting the planet's striated beauty. Conversely, Venus, which rotates retrograde and exceptionally slowly, one full rotation every 243 Earth days, possesses almost no magnetic field. Its dense carbon dioxide atmosphere insulates heat in a runaway greenhouse effect, rendering it the most scorching planet in the solar system. The juxtaposition is stark. Too rapid, and storms prevail. Too slow, and protection vanishes. Even Mars, with a day just 40 minutes longer than our own, illustrates what occurs when internal motion subsides. As its core cooled, its once formidable magnetic field disappeared, permitting solar radiation to erode its air and water. The faint traces of magnetism still persist in the crust, spectral remnants of a spin that once supported a dynamic world. Rotation, therefore, is not discretionary for habitability. It is foundational. In 2023, scientists utilizing the James Webb Space Telescope examined exoplanets like WASP-39b and TRAPPIST-1e, finding that those with quantifiable spin or atmospheric circulation display clearer indications of chemical equilibrium and temperature allocation. Without rotation, energy stays confined or is lost, fostering unstable environments. As NASA's exoplanet exploration program articulates, rotation plays a critical role in determining the climate and potential habitability of a planet. Rotation might also be linked to magnetic protection on remote worlds. A 2021 study by the Harvard-Smithsonian Center for Astrophysics indicated that exoplanets with rapid spins tend to preserve molten metallic cores longer, prolonging the lifespan of their magnetic fields. Those fields, in turn, safeguard atmospheres and may elevate the probability of surface liquid water, the essential component of life. So, when we inquire, did spinning make life possible? The data affirms yes. Rotation defines everything from a planet's day duration to its temperature gradients, atmosphere, climate, and magnetic shielding. Life, it appears, flourishes not in spite of motion, but because of it. Our world's rotational velocity has fluctuated over eons, yet its impacts continue to reverberate across time. It dictates the rhythm of tides, the proliferation of forests, the migrations of animals. It establishes our perception of time itself, not as a theoretical concept, but as the physical revolution of the world beneath us. As astrophysicist Neil deGrasse Tyson once remarked, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Pause for a moment. Attend to that revolution. Every rotation bears the whisper of 4.5 billion years of equilibrium and motion. If Earth ceased spinning tomorrow, the oceans would inundate the poles, the atmosphere would disintegrate into chaos, and the planet would lose its respiration. But tonight, as it revolves gently beneath you, everything continues to function perfectly, quietly, ceaselessly. So perhaps it is no hyperbole to state that the rotation of Earth is the quiet architect of life. The identical cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, into you. Now, as we float deeper into this odyssey, let's trace that rotation outward to where spinning no longer defines life, but starts to contort something even more peculiar. Because beyond a specific velocity, rotation does not just propel matter. It can commence to twist time itself. And that is where our subsequent chapter starts. Part 4. Can rotation distort time itself? When rotation achieves its zenith, it ceases to be motion and transforms into distortion. At extreme velocities, revolving objects no longer merely travel through space. They commence to pull at the fabric of time itself. Einstein's general theory of relativity, presented in 1915, posited that gravity and motion are indivisible, two manifestations of how mass contorts space-time. The greater the energy or spin of an object, the more profoundly it twists the geometry surrounding it. This torsion of space-time by rotation is termed frame dragging, and it stands as one of the most delicate, elegant, and validated predictions of contemporary physics. Visualize spacetime as a tranquil lake. When a massive object rotates, such as the Earth or a black hole, it agitates that lake, generating minuscule vortices in the very current of time. In those eddies, the direction of time itself can start to deviate. NASA physicist Francis Everett, who spearheaded the gravity probe B experiment, once depicted it this way. As the Earth rotates, it drags space-time around with it, much like a spinning sphere twisting the honey in which it is immersed. Gravity probe B, launched in 2004, employed 4 ultra-precise gyroscopes orbiting 400 miles above Earth to quantify this phenomenon. Following a year of observation, NASA verified that our planet's rotation drags spacetime by approximately 0.000011 degrees per year. That might seem infinitesimal, but it corresponds to Einstein's equations with phenomenal precision. Even our temperate planet, revolving once every 24 hours, is capable of distorting the flow of time. Now, envision a rotation billions of times faster and a gravitational field billions of times more potent. That is what transpires near a neutron star. When a colossal star expires, it implodes under its own gravity, compressing matter so densely that protons and electrons fuse into neutrons. The outcome is an object only about 12 miles across, but possessing a mass greater than that of our Sun. To conserve angular momentum, these stars revolve unimaginably fast, up to 700 times per second. Astronomers designate them as pulsars because their magnetic poles discharge beams of radiation that sweep across space like cosmic beacons. As they rotate, they generate the most potent known magnetic fields in the universe and contort spacetime so aggressively that even light contends to travel in linear paths. NASA's NICER instrument, situated aboard the International Space Station, has charted these distortions, revealing that time near a pulsar progresses more slowly than it does on Earth. The more potent the spin, the slower the clock. Einstein's equations inform us that this is not sorcery. It is gravitational time dilation. Time progresses more slowly in zones of stronger gravity or swifter motion. When you are proximate to a massive, spinning body, space-time itself is drawn into its rotation. You cannot remain stationary. You are dragged along as if the universe itself is revolving you. This phenomenon is particularly severe near Kerr black holes that spin. Named for the mathematician Roy Kerr, who first resolved Einstein's equations for a rotating black hole in 1963, a Kerr black hole is perhaps the most bizarre structure we comprehend. Unlike a simple, non-rotating black hole, which merely pulls everything inward, a Kerr black hole whirls spacetime around its axis. Sufficiently close to the event horizon, the velocity of that rotation nears the speed of light. Nothing, not even time, can oppose being dragged along. The zone outside the event horizon where this frame dragging transpires is termed the ergosphere. Within it, nothing can stay stationary relative to distant space. Every particle, every photon, must rotate with the black hole. It is as if space itself liquefies, spinning in a vast, imperceptible vortex. In 2021, utilizing NASA's Chandra X-ray Observatory, scientists witnessed matter spiraling around a black hole at the core of galaxy M87, verifying that it rotates near the threshold predicted by relativity. Inside that vortex, time operates differently. If you could hover securely near the ergosphere, an impossible achievement for now, your clock would tick more slowly than those on Earth. For every minute you encountered, hours could elapse for the remainder of the universe. Einstein referred to this as the warping of time, a direct outcome of motion and gravity operating in concert. As he once articulated, time and space are modes by which we think, not conditions in which we live. ESA's Event Horizon Telescope, EHT, acquired the first ever image of a black hole's shadow in 2019 and later, in 2022, released the image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. The luminous ring we observe is not illumination from the black hole itself, but from matter spiraling around it, light distorted and deferred by space-time curvature. Those incandescent arcs are visual validation that rotation and gravity combined can bend not just light, but the very progression of time. The identical laws are applicable on smaller scales, too. Even satellites orbiting Earth encounter minute time differentials. The Global Positioning System, GPS, must perpetually correct for both gravitational and velocity-induced time dilation. If left uncorrected, GPS clocks would deviate by 38 microseconds per day, sufficient to induce navigation errors of several miles. So even here, where space-time seems serene, the distortion of time is not theoretical. It is integral to daily life. When astrophysicists simulate the regions near a Kerr black hole, the mathematics becomes staggering. Rotation can contort space-time so acutely that closed time-like curves emerge, paths where a particle could, in theory, loop back to an earlier point in time. Whether these loops are physically tangible remains unresolved, but they materialize organically from Einstein's equations. In these extreme environments, past and future forfeit their established significance. The James Webb Space Telescope, with its infrared precision, now examines the accretion disks of remote quasars, galaxies fueled by supermassive rotating black holes. JWST's spectra reveal light from these disks elongated and redshifted, an indication that time progresses more slowly in those zones. Some of the light we register today departed those spinning behemoths over 13 billion years ago, meaning we are observing time itself elongated across the cosmos. Rotation, it materializes, does not just define matter. It dictates how time flows near it. The swifter and denser the spin, the more profound the warping of spacetime. From our temperate planet to the ferocious hearts of galaxies, the universe employs spin to sculpt both motion and time. What we designate as now is distinct everywhere, contingent on how fast and how deep the local spacetime is revolving. Even light, which typically travels at the universe's ultimate velocity threshold, is compelled to bend and decelerate near rotating masses. NASA's NuSTAR and XMM Newton missions have captured X-ray echoes surrounding black holes, light momentarily trapped in rotation before breaking free. In these echoes, time elongates like a delicate thread. Quantifiable, predictable, yet endlessly peculiar. One might contemplate then whether the universe itself is twisting time on a monumental scale. Large-scale cosmic rotation could subtly affect the way time progresses across billions of light years. While current cosmological data from ESA's Planck satellite indicates no compelling evidence for universal spin, the query remains unresolved. Even the faintest torsion over cosmic distances might leave imprints in the polarization of ancient light, clues that time itself possesses a preferred direction. As physicist Kip Thorne, co-author of The Science of Interstellar, clarified, in the warped spacetime near a spinning black hole, the future of one observer can become the past of another. Rotation doesn't just bend trajectories. It bends the sequence of events, the very rhythm of existence. And yet, for all its peculiarity, the effect is consistent and quantifiable. Time dilation around rotating bodies has been confirmed by atomic clocks aboard aircraft, satellites, and in high-altitude laboratories. The faster you journey, or the deeper you descend into gravity, the slower your time progresses. It is not an illusion. It is the universe maintaining flawless equilibrium. So yes, rotation can bend time. But what is even more compelling is why that bending appears to adhere to a pattern, a fluid, universal law that connects motion, gravity, and energy into one continuum. From Einstein's equations to every ticking satellite, it all indicates one truth. The universe does not just travel through time, it generates it through motion. Take a slow breath. Right now, your own perception of time is tethered to Earth's gentle spin, the sun's pull, the galaxy's revolution. You are enveloped by motion so precise, it dictates the very seconds you inhabit. And if rotation can distort time, what transpires when time begins to control the spin? That is the enigma awaiting us in our next chapter. Part 5. If spin governs time, who governs the spin? Every second you experience is defined by motion. The ticking of your watch, the pulse of an atomic clock, even the rhythm of your own heartbeat, all rely on something revolving. Electrons rotate within atoms. The Earth revolves once every 24 hours. And as it spins, it drags spacetime just sufficiently to alter how time progresses. At the equator, where Earth's surface moves fastest, about 1,037 miles per hour, clocks operate slightly slower than those situated at the poles. It is not due to temperature or air pressure. It is due to relativity. Einstein's theory demonstrated that motion and gravity can elongate or compress time, contingent on how fast and how deep you are within a gravitational field. So yes, spin governs time. But the query persists. Who or what governs spin? Music. To resolve that, scientists examine the most dependable keepers of time humanity has ever constructed: atomic clocks. Within them, electrons whirl around atomic nuclei at predetermined energy levels. When they transition between those levels, they discharge photons at a precise frequency. That frequency, defined by the cesium-133 atom, establishes the duration of 1 second. 9,192,631,770 cycles of radiation, corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. Those words, published by the International Bureau of Weights and Measures, describe how every second of your existence is calibrated to a minuscule atomic spin. The rotation of electrons inside atoms is a form of quantum spin, not a physical twirling, but a foundational property of matter. In quantum mechanics, particles possess spin values that dictate how they operate in magnetic fields, how they bond, and even how they adhere to the Pauli exclusion principle, the regulation that no two electrons can occupy the identical quantum state. So at its most infinitesimal scale, timekeeping relies on spin, not the revolution of a planet, but the internal angular momentum of atoms themselves. But just as atomic spins regulate time within our laboratories, planetary spins regulate time on a cosmic level. The Earth's rotation establishes the duration of a day, while its orbit around the Sun establishes the duration of a year. These motions are not static. They incrementally drift. Tidal forces from the Moon are progressively decelerating Earth's spin, adding 1.7 milliseconds per century to each day. To maintain synchronization between atomic time and planetary time, scientists employ a system known as leap seconds. Periodically, the world's atomic clocks are modified by 1 second to align with the planet's innate rotation. In a way, we are perpetually recalibrating human time to correspond with Earth's cosmic spin. If you compare clocks at varying latitudes, the distinctions are quantifiable. A clock situated at sea level near the equator, moving fastest due to Earth's spin, operates marginally slower than one positioned high in the mountains or near the poles. This is both special and general relativity in action. As NASA clarifies, a clock on the equator ticks more slowly than one at the poles because it's moving faster and deeper in Earth's gravitational potential. The variance is tiny, a few nanoseconds per day, but tangible. Your phone's GPS system must correct for this phenomenon constantly. Each of the 24 GPS satellites orbits Earth at approximately 8,700 miles per hour, 12,500 miles above the surface. In orbit, they encounter weaker gravity and higher velocity, causing their onboard atomic clocks to run faster by about 38 microseconds per day. If uncorrected, this would cause navigation errors of several miles to accrue every few hours. To maintain time consistency, engineers merge Einstein's equations with real-world quantifications, literally compensating for the curvature of spacetime induced by Earth's rotation. So every time you consult a map or receive a location signal, you are observing relativity in motion, a quiet synergy between gravity, motion, and spin. But who initiated the spin in the first instance? Astronomers trace it back to angular momentum, a conserved quantity in physics. When the solar system materialized 4.6 billion years ago, a cloud of gas and dust imploded under gravity. As it condensed, it spun faster, just like a skater retracting her arms. That primordial motion allocated angular momentum to everything within: the sun, the planets, their moons. Each entity still possesses a fraction of that ancient rotation. No external force perpetually maintains their spinning. They persist because of inertia. the identical law that keeps a planet in motion until something opposes it. In space, where friction is virtually non-existent, spins can endure for billions of years. So the answer to who controls spin is no one. Once initiated, the universe requires no hand to keep revolving. But the correlation between spin and time becomes more peculiar the deeper we investigate. Inside atoms, spin dictates energy states. On planetary scales, spin establishes days. On cosmic scales, spin drags time itself. And all these levels are interconnected by one law. Angular momentum is conserved. Time, in that respect, is not an autonomous entity. It is a mirror of how energy and spin engage. In 2016, ESA's Gaia mission charted the precise motions of over 1 billion stars in the Milky Way. The data indicated that our entire galaxy revolves once every 230 million years, transporting the Sun and its planets along in a vast spiral. Each star's orbit contributes to a grand cosmic timepiece. One rotation signifies the rhythm of galactic time. Just as atomic spin establishes seconds, stellar spin establishes eons. Even the Sun rotates once every 27 days at its equator, but not consistently. Its poles revolve slower, a phenomenon termed differential rotation. This twisting motion generates magnetic fields that sculpt solar flares and coronal mass ejections. When those magnetic tempests reach Earth, they contort our own magnetic field and can even impact satellites and power grids. So from the atomic scale to the solar scale, spin is not passive. It sculpts fields, establishes rhythms, and engages with the very instruments we utilize to quantify time. Einstein's relativity linked these patterns beautifully. In his equations, the geometry of spacetime relies on energy and momentum, including angular momentum. In different terms, spin curves time. If you eliminate spin, spacetime becomes simpler, flatter, less dynamic. Incorporate spin, and it warps, gently for planets, aggressively for black holes. We might then assert that time itself is documented in motion. The second is inscribed in atomic spin, the day in planetary spin, the cosmic epoch in galactic spin. Everything that moves quantifies, and everything that quantifies moves. In 2022, the James Webb Space Telescope viewed distant galaxies whose light has journeyed over 13 billion years. Even in those primordial galaxies, astronomers identified rotation, an indication that angular momentum was present almost immediately after the Big Bang. That signifies the law connecting spin and time has been operational since the universe's nascent seconds. Spin is not a consequence of time. It is part of what imparts time with its progression. So if spin regulates time, and spin itself emerges organically from the conservation of motion, then who or what controls it? The most precise answer science can provide is, the universe controls itself. Every spin is counterbalanced by another. Every decelerating motion is matched by an exchange of momentum elsewhere. Even the most infinitesimal quantum particle adheres to these same equations, guaranteeing that angular momentum stays perfectly conserved across space and time. NASA's Jet Propulsion Laboratory articulated it simply. The laws of motion do not alter. The universe operates on equilibrium. What is forfeited in one location is acquired in another. There is no master clock, no concealed hand. The very act of motion preserves its own timing. Spin, then, is the universe's internal gyroscope, its inherent mechanism for keeping everything aligned. From your atoms to the stars above, the identical principle regulates every scale. Even when systems degrade, collide, or decelerate, their angular momentum transfers onward, keeping the cosmic clock ticking. And so, when you inquire who controls the spin, the universe gently replies, no one must. Motion is self-perpetuating. It is the quiet equilibrium that underpins both time and existence. Take a breath. The atoms within you spin in synchronization with the revolving Earth, the orbiting moon, the spiraling galaxy. You are already an element of that motion. Every heartbeat, a fraction of a universal rhythm that commenced long before clocks, calendars, or light itself. Music. And as that rhythm persists, another query gradually surfaces. Not, who is in control? One that extends beyond motion into the framework of the cosmos itself. If the universe relies on flawless equilibrium, what transpires when that symmetry fractures? That is where we float next. Part 6. Did the universe commence because symmetry was fractured? If everything had once been perfectly in balance, nothing would ever have moved. No stars, no atoms, no time, only stillness, unending and unaltered. But the universe we comprehend began not with flawlessness, but with a minute imperfection, a small fissure in symmetry that permitted everything to materialize. In physics, symmetry signifies that the laws of nature operate the same way in every direction, at every point, and for every observer. When symmetry holds perfectly, nothing possesses a rationale to change. But when it fractures, even fractionally, motion materializes, structure surfaces, and time acquires direction. As NASA's Goddard Space Flight Center portrays it, the universe exists as we know it because perfect symmetry didn't last. Let's drift back to the initial fractions of a second following the Big Bang. According to the standard model of particle physics, the nascent universe was a hot, dense plasma where the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were momentarily unified. But as the universe expanded and cooled, these forces started to diverge. This procedure, termed spontaneous symmetry breaking, defined everything from the architecture of atoms to the structure of spacetime itself. The Planck mission charted the cosmic microwave background, the faint afterglow of the Big Bang, and discovered it was remarkably uniform, yet not perfect. Minute variations in temperature, only 1 part in 100,000, disclose the first indications of fractured symmetry. Those infinitesimal distinctions in energy density subsequently evolved into galaxies, stars, and planets. Lacking those fluctuations, the universe would stay smooth and static, an unending, featureless vapor. Even matter itself attributes its existence to fractured symmetry. When the universe was young, it generated matter and antimatter in nearly equivalent quantities. But nearly is the pivotal word. For every billion particles of antimatter, there were 1,000,000,001 of matter. That fractional imbalance, known as baryon asymmetry, signified that when matter and antimatter neutralized each other, a tiny portion of matter endured. That residual matter became the stars, the planets, and everything we observe today. In 1964, physicists James Cronin and Val Fitch discovered this subtle asymmetry in particle behavior, an effect now termed CP violation. Their experiment with neutral kaons demonstrated that the laws of physics regard matter and antimatter marginally differently. This finding secured them the Nobel Prize and offered the first indication that the universe favors one direction, one spin, one imbalance. As ESA's Particle Physics Division observes, without CP violation, the universe would contain no matter, only light. So, in a sense, imperfection rendered everything possible. The mechanism underlying this imbalance is still under investigation. At CERN, the Large Hadron Collider probes particles like the Higgs boson, which assumes a vital role in fracturing electroweak symmetry. When the universe cooled below a critical threshold, about 10 to the power of -12 seconds after the Big Bang, the Higgs field acquired a non-zero value everywhere in space. That field imparts particles with mass and fractures the symmetry between light and matter. It is often stated that the Higgs field is what solidified the universe into its current configuration, locking in the distinctions that made complexity viable. But not all symmetry breaking is aggressive. Occasionally it is gentle, like the way a perfectly balanced pencil will ultimately descend in one specific direction. The universe may have selected a direction for time in a comparable fashion. In the nascent instance, time could have progressed equally forward or backward. But a tiny fluctuation, perhaps in entropy, perhaps in quantum probability, propelled it forward, establishing the arrow of time. As physicist Sean Carroll once documented, the arrow of time is the result of low entropy at the beginning of the universe, a state of broken symmetry that all later moments remember. So when we quantify time, we are truly quantifying how far we have drifted from flawless symmetry. Even the cosmic web, the vast framework of filaments connecting galaxies, emerges from this imbalance. JWST's deep field images reveal galaxies materializing along imperceptible threads of dark matter that trace the earliest quantum fluctuations in density. Those fluctuations initiated as random variations, amplified by cosmic inflation just moments following the Big Bang. What commenced as tiny irregularities became the architecture of the universe. Without a symmetry, gravity itself could not operate the way it does. A perfectly uniform allocation of matter would pull equivalently in all directions, yielding no motion. But with slight unevenness, gravity could engage, drawing matter into clusters, forming galaxies, stars, and ultimately planets. NASA's WMAP mission described it succinctly. If the early universe had been perfectly smooth, no structure could have formed, no galaxies, no stars, no life. Even at the quantum scale, particles betray the identical imbalance. Neutrinos, for example, are known to possess chirality. They all spin in the same left-handed direction. This handedness of the universe may be another resonance of the original symmetry breaking. It is a pattern that recurs from the most infinitesimal scales to the largest, from subatomic spins to galactic rotations. Everywhere we investigate, the universe displays preference. Galaxies revolve clockwise or counterclockwise in unequal proportions. Molecules of life, like amino acids and sugars, exhibit handedness too, a bias termed chirality that underpins all biology. Although life emerged billions of years after the Big Bang, its chemistry still mirrors the same ancient asymmetry inscribed into the structure of the cosmos. This link between cosmic imbalance and biological structure captivates scientists. A 2020 study by the Astrobiology Institute at NASA suggested that polarized ultraviolet light from nascent stars may have eradicated right-handed amino acids, permitting left-handed ones to prevail on Earth. If correct, then even life's molecular spin owes its direction to the universe's first fractured symmetry. But perhaps the most refined demonstration of this principle rests in the cosmic microwave background's polarization. The Planck satellite identified tiny swirls, B-mode polarization, that may hint at primordial gravitational waves. These waves would be the imprints of inflation, the universe's first, fastest spin, and the instant when symmetry yielded to motion. If verified, they would be direct proof that the universe's very first act was to fracture perfect balance. From the way light bends to the way galaxies align, everything we quantify points back to that singular principle. Imperfection propels creation. Symmetry is elegant but delicate. Fracture it slightly, and the universe awakens. As theoretical physicist Murray Gell-Mann once remarked, if the world were perfectly symmetrical, there would be nothing. It is the deviations, the slight distinctions in energy, in motion, in charge, that render reality viable. When we observe the universe through telescopes like JWST, what we are truly witnessing is the fossil record of fractured symmetry, the first flicker of imbalance that transformed into time, structure, and light. And from that faint imperfection, everything else ensued: galaxies, planets, oceans, and the quiet, rotating world beneath your feet. Take a slow breath. You are living validation of asymmetry, a being crafted from matter that once outnumbered its mirror twin by just 1 in a billion. Every atom in your body carries the remnant of that cosmic bias, preserved since the first microseconds of existence. So yes, the universe commenced because symmetry fractured. Perfection yielded to motion, and motion gave rise to time. A small fissure in equilibrium created everything that would ever spin, shine, or breathe. And as we trace that first imbalance outward, we encounter a new enigma, a query not about origins, but about what binds the cosmos despite its unceasing motion. Because if galaxies spin faster than they ought to, something imperceptible must be securing them in place. And from that imbalance, a new mystery starts to revolve, one concealed in the blackness between galaxies. Part 7. What binds galaxies when they spin too fast to cohere? Galaxies revolve at improbable velocities. Stars on, their peripheral edges move so rapidly that by all statutes of physics, they should fly apart, dispersed like embers from a turning wheel. And yet they do not. Something imperceptible is securing them in place. A silent mass that dwarfs everything we can observe. Astronomers term it dark matter. It doesn't radiate, reflect, or absorb light. It doesn't collide, liquefy, or constitute atoms. But it gravitates, it pulls, and that invisible pull prevents entire galaxies from disintegrating. The enigma commenced in the 1930s when Swiss astrophysicist Fritz Zwicky analyzed the Coma cluster, a vast collection of more than 1,000 galaxies drifting 320 million light-years away. Zwicky quantified how rapidly the galaxies were moving and discovered that their apparent mass, the stars, gas, and dust, was not remotely sufficient to bind them. The cluster should have propelled itself apart eons ago. He posited something astounding. An unseen mass must be present, furnishing the absent gravity. He labeled it Dunkle Materie, dark matter. For decades, his concept lingered as a whisper until the 1970s, when American astronomer Vera Rubin started quantifying the rotation curves of spiral galaxies, utilizing data from the Kitt Peak National Observatory in Arizona. Rubin discovered that stars distant from galactic centers were orbiting just as rapidly as those near the core, a finding that contradicted Newtonian physics. According to gravity alone, orbital velocities should decrease as you move outward, just as planets distant from the Sun move slower. But Rubin's graphs were horizontal. Every star, from the center to the periphery, moved at nearly the identical velocity. Something unseen was furnishing supplemental gravity across the galaxy. As NASA later articulated, the rotation curves of galaxies tell us there's much more mass than meets the eye. That mass, dark matter, now seems to constitute about 85% of all matter in the universe, roughly 5 times more than the visible matter that comprises stars, planets, and people. Scientists project that galaxies reside within vast dark matter halos, imperceptible spheres stretching far beyond their visible boundaries. Each halo functions as scaffolding, binding stars and gas together via gravity. Without it, galaxies like the Milky Way would disintegrate in a few million years. Simulations from NASA's Goddard Space Flight Center illustrate that dark matter provides the cosmic adhesive that permits galaxies to materialize, fuse, and endure. The European Space Agency, ESA, has also long observed this invisible framework through gravitational lensing, the distortion of light by massive objects. When light from remote galaxies travels near a cluster saturated with dark matter, the unseen mass warps spacetime, amplifying and contorting the background light into elegant arcs. The Euclid mission, launched in 2023, is engineered to chart this effect across billions of galaxies, fashioning the most intricate 3D map of dark matter ever produced. Even preceding Euclid, the Hubble Space Telescope provided us stunning insights of this cosmic lensing. In 2006, Hubble imaged the Bullet Cluster, where two galaxy clusters had collided. X-ray images from NASA's Chandra Observatory revealed that the hot gas, ordinary matter, trailed behind following the collision. But when scientists charted the total mass utilizing gravitational lensing, the majority of it lay ahead, detached from the visible matter. It was unequivocal proof that most of the mass was imperceptible, an autonomous, unseen component of the universe. Dark matter does not engage with light or electromagnetic forces, which is why it cannot be observed directly. It engages only via gravity and potentially the weak nuclear force. The primary candidates are hypothetical particles such as WIMPs, weakly interacting massive particles, or axions, both posited by extensions of the standard model of physics. Experiments like Xenon-T in Italy and Lux Zeppelin in South Dakota are attempting to identify these particles through infrequent collisions with atomic nuclei. Thus far, no confirmed identification has been achieved, but the pursuit persists quietly deep underground, shielded from cosmic rays. Meanwhile, NASA's Fermi Gamma Ray Space Telescope has sought subtle signatures of dark matter annihilation in the centers of galaxies. And JWST has commenced observing the faint structures of galaxies in the nascent universe, less than 400 million years after the Big Bang. Even at that young epoch, galaxies already displayed stable rotation, implying that dark matter halos were already established. As ESA scientists documented, dark matter must have formed early, shaping the universe long before the first stars ignited. On cosmic scales, dark matter dictates not only how galaxies revolve, but how the universe progresses. Computer simulations like NASA's Illustris and Eagle projects demonstrate that without dark matter, galaxies would never materialize. Matter would stay uniformly distributed, unable to aggregate under gravity. Dark matter furnished the imperceptible scaffolding upon which visible matter condensed. It is, as astrophysicist Neil deGrasse Tyson described it, the greatest cosmic mystery of our time, a shadow universe holding ours in its grip. Though imperceptible, dark matter leaves a trace everywhere. It defines galaxy clusters, influences cosmic filaments, and even affects the manner in which the universe expands. Dark matter doesn't discharge radiation, but its gravity decelerates the outward expansion that commenced with the Big Bang. This cosmic tug-of-war between dark matter's gravity and dark energy's acceleration defines the large-scale framework of everything. So, how rapidly are galaxies truly spinning? Consider our Milky Way. The Sun orbits the galactic center at about 14,000 miles per hour, finalizing one rotation every 230 million years. At that velocity, and given the visible mass we can tally, our galaxy should have disintegrated long ago. But the dark matter halo enveloping it, stretching perhaps 200,000 light-years beyond the visible disk, contributes the requisite mass to maintain its integrity. This equilibrium between spin and gravity is delicate. If dark matter were just marginally less prevalent, galaxies would disperse. If marginally more, they would implode under their own mass. ESA's Planck satellite approximates the universe's makeup as 68% dark energy, 27% dark matter, and only 5% ordinary matter. So everything we can observe, every star, planet, and person, accounts for just 1/20th of what actually exists. What renders dark matter so confounding is that it does not fit tidily into our established physics. We can quantify its gravitational pull, chart its distribution, and simulate its impacts, but we cannot yet identify what it comprises. Some physicists even posit that our comprehension of gravity itself might necessitate revision. Modified theories like MOND, modified Newtonian dynamics, and TIVUS attempt to elucidate galaxy rotation without dark matter. But thus far, dark matter persists as the simpler, more coherent explanation. New missions endeavor to resolve this enigma. ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will operate in tandem to map billions of galaxies and quantify how dark matter has defined their evolution over 13 billion years. Their objective is not merely to comprehend dark matter, but also to uncover how it engages, or doesn't, with dark energy, the enigmatic force propelling the universe's expansion. Even the James Webb Space Telescope contributes to this endeavor. By observing the most nascent galaxies, JWST permits scientists to test whether dark matter operates the same way across cosmic epochs. If the formation of those early systems corresponds to current models, it fortifies the case that dark matter's imperceptible hand has perpetually been at work. It is strange to consider that what maintains galaxies' integrity is something we cannot see or touch. Yet, its gravitational melody holds the cosmos in harmony. Without it, the universe would forfeit its shape, its stars propelled into blackness, its clusters unbound. Dark matter is the quiet architecture of existence, a framework constructed not of light, but of stability. Take a breath. Every star you have ever observed, every galaxy that floats across your telescope, is balanced upon something invisible. You are inhabiting a universe held together by shadows, forces that act without being perceived, steering the motion of everything that spins. And as we trace that imperceptible hand through the blackness, we start to observe something even more peculiar. If dark matter binds galaxies, could it also have defined the direction of life itself, even down to the spin of molecules? Perhaps the same concealed force that binds galaxies also left its imprint within the spirals of life, a trace we are about to reveal. Part 8. Does the universe's spin dictate the direction of life? Every living entity on Earth is contorted just fractionally. Your DNA spirals to the right. The amino acids that construct every cell in your body bend to the left. This one-sidedness, termed chirality, is one of the most profound mysteries in biology. It signifies that life, down to its most infinitesimal molecular configuration, has a favored direction, a bias, a spin. In chemistry, chirality signifies handedness. Just as your left and right hands are mirror reflections that cannot be perfectly superimposed, certain molecules exist in two configurations, one left-handed and one right-handed. In most chemical reactions, both versions can materialize equally, but in living organisms, only one hand is ever selected. DNA and RNA invariably twist to the right. Amino acids, which constitute proteins, invariably twist to the left. It is as if, long ago, life reached a permanent determination and has adhered to that spin ever since. Scientists have dedicated decades attempting to comprehend why. If chemistry alone can yield both directions equally, then something external to biology must have prodded life toward one side. One potential indication originates from the light of ancient stars. Light waves can be polarized, signifying they oscillate more robustly in one direction than another. In the nascent universe, young, massive stars discharged intense ultraviolet radiation that became circularly polarized as it dispersed through magnetic dust clouds. According to research undertaken by NASA's Astrobiology Institute and Ames Research Center, this polarized light could preferentially eradicate one type of amino acid more than the other. Over millions of years, that subtle preference may have seeded the handedness of life itself. The European Space Agency's Rosetta mission contributed evidence to this hypothesis. When Rosetta's Philae lander settled down on Comet 67P Churyumov-Gerasimenko in 2014, it identified complex organic molecules, including amino acid precursors. Analysis of their structure revealed signs of asymmetry, hinting that chiral bias may have been present before life commenced on Earth. That signifies the direction of life's molecules could have been inherited from interstellar chemistry, defined by cosmic light and motion, long before our planet even materialized. Another indication comes from meteorites. In 1969, the Murchison meteorite descended in Australia. It housed more than 70 different amino acids, and scientists subsequently discovered a slight surplus of left-handed configurations. As NASA's Johnson Space Center clarified, the Murchison meteorite safeguards chemical imprints from before the solar system formed. Those imprints reveal that the universe already possessed a favored molecular direction, one that life would subsequently embrace. Why left for amino acids and right for DNA? It might be more than mere chance. Some researchers posit the opposing orientations actually complement each other, one dictating structure, the other stability. Left-handed amino acids fold proteins that can bond flawlessly with right-handed nucleic acids, establishing the biochemical harmony that supports life. Invert that orientation, and the chemistry simply fails to operate as proficiently. Still, this asymmetry did not surface stochastically. It may trace back to the most nascent quantum imbalances, fluctuations in energy and spin that transpired within microseconds following the Big Bang. Experiments at CERN and Fermilab have verified that some subatomic particles, such as neutrinos, invariably spin in a left-handed direction. This universal handedness, or parity violation, demonstrates that even fundamental physics is not perfectly symmetrical. In 1956, physicists Qiansheng Wu and Sungdao Li validated this through their historic beta decay experiment. They demonstrated that the weak nuclear force, one of the four fundamental forces, does not regard left and right equivalently. As Wu herself depicted, nature is not as symmetrical as it appears. If even the universe's foundational forces favor one spin over another, then it is not difficult to conceive that life's molecules, too, inherited this cosmic preference. On Earth, this pattern persists everywhere we observe. From the swirling arms of hurricanes to the spiraling development of shells, spin and asymmetry are integrated into nature's blueprint. The Coriolis effect, prompted by Earth's rotation, dictates the direction of large-scale tempests, counterclockwise in the northern hemisphere, clockwise in the southern. Even our planet's magnetic field possesses a defined polarity, reversing occasionally but never forfeiting its sense of direction. The farther we gaze into space, the more this cosmic bias re-emerges. In 2011, astronomer Lior Shamir studied tens of thousands of galaxies utilizing data from the Sloan Digital Sky Survey. He discovered a minor but substantial distinction in the quantity of galaxies rotating clockwise versus counterclockwise. That imbalance implied a large-scale directional pattern, perhaps a remnant of the universe's nascent spin. If correct, then the identical asymmetry that regulates galaxies may resonate all the way down to the molecular structures of life. This link between cosmic motion and biochemistry has captivated scientists for decades. A 2021 study from the Tokyo Institute of Technology simulated the impacts of circularly polarized light on amino acids in interstellar environments. They discovered that even a minor imbalance in photon spin could precipitate a quantifiable distinction in molecular chirality. In different terms, light defined by cosmic rotation might have literally established the direction of life. It is simple to overlook that light itself possesses spin. Photons can have right-handed or left-handed polarization, a form of angular momentum that influences how they engage with matter. When early starlight traversed magnetic fields twisted by rotation, that spin could impress a bias onto the molecules it contacted. Even the most basic dust grains floating between stars might have been polarized by galactic motion, scattering light in a manner that favored one molecular hand over the other. The James Webb Space Telescope is now analyzing complex organics in star-forming regions like the Taurus Molecular Cloud and the Orion Nebula. JWST's infrared instruments have identified prebiotic compounds, including carbon chains and nitriles, materializing under the influence of polarized starlight. These observations imply that the chemical seeds of life naturally inherit directionality from their cosmic surroundings. So when we inquire whether the universe's spin dictated the direction of life, the evidence indicates a quiet yes. From the spin of galaxies to the handedness of neutrinos, from polarized light to chiral molecules, every scale of nature appears to favor motion in one direction. It is as if life is not stochastic at all, but a continuation of the universe's most nascent rotation, inscribed into every strand of DNA. As astrophysicist Carl Sagan once remarked, "We are made of star stuff." Perhaps we are also made of the spin of those stars, the angular memory of their light. Take a quiet breath. Every cell inside you still possesses that twist, a microscopic resonance of the universe's revolution. From the dance of galaxies to the spiral of your DNA, the identical motion persists, smooth and silent across billions of years. And now, as we investigate deeper into that cosmic interconnection, another query surfaces. Not about origins, but about conclusions. If everything that spins must one day decelerate, what transpires when the universe itself forgets how to turn? That is the enigma waiting quietly ahead. Part 9. Will the universe forget how to spin? Every rotation decelerates. The Earth's days are becoming longer. Galaxies are drifting apart, their elegant spirals forfeiting momentum. Even the stars themselves, those furnaces of motion and fusion, are extinguishing one by one. The universe that commenced with a great spin seems slowly to be unwinding. But can motion genuinely cease? Or does it merely diminish, spreading thinner and thinner across the structure of space? NASA physicist Michelle Thaler once stated, "Energy doesn't disappear, it disperses. So too with spin. It doesn't halt, it diffuses." Our planet, for example, is already losing its cadence. Each century, the Moon's gravitational pull decelerates Earth's rotation by about 1.7 milliseconds, transferring energy outward. The outcome is that the Moon drifts away by nearly 1.5 inches every year, a gentle choreography that has endured for billions of years. Laser reflectors positioned on the lunar surface by Apollo astronauts verify this drift with millimeter precision. If this procedure persists, Earth's rotation will one day synchronize with the Moon's orbit, each perpetually presenting the same face to the other, as the moon already does to us. It will signify the end of tides as we comprehend them, the end of the daily cycle of ocean and air. Planetary spin, once vibrant, will fade into equilibrium. Elsewhere in the solar system, the identical narrative unfolds. Mercury is already confined in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits around the Sun. Venus, with its dense atmosphere, has decelerated to an almost unnatural crawl. 1 rotation every 243 Earth days, and in the opposite direction of its orbit. Even Mars, whose day is only marginally longer than ours, is progressively losing speed. Over cosmic timescales, spin is not perpetual. It is a rhythm winding down. The deceleration continues beyond planets, into the core of galaxies. Utilizing the Hubble Space Telescope and the Very Large Telescope, VLT, astronomers have quantified the rotation of spiral galaxies billions of light-years distant. When juxtaposed with contemporary galaxies, those ancient systems appear to have spun faster, tighter arms, denser cores, more angular momentum. As time elapses, gravitational interactions and cosmic expansion progressively drain that motion. According to a 2020 study from the Leibniz Institute for Astrophysics Potsdam, galaxies may forfeit a portion of their spin through collisions and fusions. When 2 galaxies fuse, their stars do not collide, but their dark matter halos engage, redistributing angular momentum outward. This procedure leaves galaxies rounder, slower, and more diffuse, the spiral yielding to the ellipse. The European Space Agency's Gaia mission has charted over 1.8 billion stars in the Milky Way, revealing that even our galaxy is progressing toward stillness. Its outer arms, once securely wound, are progressively elongating. Over billions of years, friction with dark matter and adjacent galaxies will drain its spin, softening its spiral configuration. Ultimately, the Milky Way and Andromeda will collide, not in mayhem, but in slow, silent fusion. Their blended rotation will resolve into a singular, massive, nearly motionless elliptical galaxy. But spin does not cease when the stars dim. It transforms. When a colossal star expires, it implodes inward, conserving angular momentum and spinning faster than ever before. This generates neutron stars, city-sized objects that can revolve hundreds of times per second. NASA's NICER instrument on the International Space Station has observed pulsars spinning 716 times per second, their beams sweeping through space with the precision of atomic clocks. Yet even these cosmic beacons ultimately decelerate, radiating away energy as gravitational waves and magnetic fields. As time expands further, rotation becomes infrequent. Stars dim. Black holes, the last great engines of spin, slowly dissipate through Hawking radiation. In 1974, Stephen Hawking posited that even black holes are not everlasting. They leak energy and forfeit angular momentum over inconceivable timescales. A spinning black hole, known as a Kerr black hole, progressively transfers its rotation to ambient space, leaving faint ripples of energy that stretch across the universe. The LISA mission, slated for the 2030s, will identify these gravitational whispers, waves prompted by spinning black holes fusing and diminishing. Each identification will be a record of rotation being discharged into spacetime, reverberating across billions of light-years. Even when the black holes themselves are extinct, their rotational memory will stay imprinted in the geometry of the universe. So, will the universe ever genuinely cease spinning? Not entirely. Angular momentum cannot be annihilated, only spread thinner, distributed among an ever-expanding sea of particles. As NASA clarifies, in an isolated system, angular momentum is conserved. The universe, in this respect, never ceases moving. It only redistributes motion. Still, there may arrive an epoch when motion becomes imperceptible. In the remote future, long after the last stars have expired and galaxies have diminished, the universe will enter what physicists term the heat death. Energy will be uniformly allocated. There will be no temperature gradients, no progression, no rationale for anything to move. Rotation will endure mathematically, but without contrast or structure, it will possess no significance. Some cosmologists, including Lawrence Krauss and Brian Greene, depict this as the cosmic silence, the ultimate calm after every vibration, every orbit, every spin. In that remote epoch, protons themselves may degrade and black holes may diminish into bursts of radiation. Only faint background photons and neutrinos will float endlessly through space, bearing the last traces of the universe's once grand rotation. The James Webb Space Telescope peers deep into the past, but it also reminds us of the universe's future. Every ancient galaxy it observes is another tick backward on the cosmic clock, illustrating how rotation once defined structure. In its images, we see both origins and conclusions, motion ignited by imbalance and motion diminishing into stillness. Even so, spin leaves imprints that cannot be eradicated. From the polarization of the cosmic microwave background to the curvature of spacetime around dying stars, the memory of motion stays encoded in the universe's blueprint. It is not movement we forfeit, only the capacity to perceive it. Take a long, slow breath. Right now, the Earth's core still revolves. The stars still orbit, and the Milky Way still floats through the blackness. Every motion you recognize is a flicker of that ancient rotation, one that will outlast you, but not eternity. And when that eternity materializes, when the last spin finally elongates into silence, something else will still endure. Not movement, but the memory of movement. Because even when the universe forgets how to turn, its geometry will still recollect that it once did. As we near that horizon of stillness, another query quietly materializes. If every atom, every planet, every galaxy is decelerating, what does that make us? The ones still moving within it. That is where our next narrative commences, with motion not of the cosmos but of consciousness itself. Part 10. Are we the universe recollecting its own motion? Every atom inside you is revolving. The electrons orbiting your nuclei, the protons and neutrons within them, the quarks deep inside, all are ensnared in ceaseless motion. That motion is not stochastic. It is a continuation, the faint resonance of the universe's inaugural rotation. When you move, when you inhale, when your heart pulses, you are not detached from the cosmos. You are integral to its most ancient memory, motion itself. In physics, angular momentum is the persistence of spin, the regulation that maintains motion's vitality. It is why galaxies still revolve, why planets still orbit, and why atoms still vibrate after 13.8 billion years. According to NASA's Goddard Space Flight Center, angular momentum cannot be annihilated, only transferred or distributed. That signifies every spin in the universe, from the most grandiose to the most infinitesimal, is a continuation of the same primordial rotation that commenced at the Big Bang. In the beginning, the universe was not static. Quantifications from ESA's Planck satellite reveal that the cosmic microwave background, the faint afterglow of the Big Bang, possesses subtle anisotropies, slight directional distinctions in temperature. Some cosmologists construe these as traces of the universe's first angular momentum, the original torsion that set everything in motion. That primordial spin never ceased. It fragmented, distributing across scales from galaxies to atoms. When stars materialize, clouds of hydrogen and helium implode under gravity. As they condense, they rotate faster, conserving angular momentum like an ice skater retracting her arms. This identical regulation gives rise to accretion disks around nascent stars, planetary systems, and even black holes. Each planet, each moon, bears a fragment of that spin embedded in its orbit. And within those planets, inside every rock, ocean, and living cell, the pattern persists at smaller scales. Our atoms, too, retain rotational memory. The electrons that establish chemical bonds adhere to the quantum property of spin, a foundational angular momentum intrinsic to all particles. This spin is not literal revolution, but a quantum state, a value that dictates how particles engage with magnetic fields. Without it, chemistry would not materialize. NASA's Quantum Laboratory Initiative depicts spin as the engine of atomic structure, the difference between chaos and stability. In this respect, you could assert every piece of matter bears an ancient choreography. The spin of particles precipitates magnetic fields, which precipitate structure, which precipitates stars and planets and ultimately life. Your neurons discharge using electrical potentials defined by these identical fields. Every thought that traverses your mind is an alignment of charged particles, a form of ordered motion. So when we inquire whether consciousness might be the universe recollecting its motion, the query is not poetic. It is physical. Each brain wave, each signal, is constructed upon rotations that have been present since the dawn of time. The magnetic fields generated by your neurons are faint resonances of the identical electromagnetic principles that steer pulsars and magnetars. As astrophysicist Neil deGrasse Tyson stated, "We are not in the universe, we are part of the universe, and the universe is in us." From a scientific viewpoint, memory is a form of pattern preservation, information encoded in physical states. Atoms remember through spin orientation. Cells remember through molecular structure. Stars remember through rotation curves. And the universe remembers through the geometry of spacetime itself. Einstein's general relativity instructs that energy and momentum define spacetime's curvature. Every movement, every rotation, leaves a minor indentation, a swirl in the geometry of reality. This is recognized as frame dragging, verified by NASA's Gravity Probe B experiment in 2011. The probe quantified how Earth's rotation subtly twists the ambient spacetime like a spoon agitating honey. It validated that spin is not confined to objects. It permeates the very structure of the cosmos. In a comparable fashion, even your movements, though infinitesimal, also disrupt spacetime ever so slightly. The distinction is merely scale. Your body's atoms spin billions of times per second, generating magnetic interactions quantifiable by quantum sensors. Each micro-rotation contributes to the ongoing documentation of motion that commenced long before humanity arose. If all motion leaves remnants in spacetime, then perhaps what we term awareness is the mechanism by which the universe perceives those remnants through us, not as an emotion or spirit, but as physical continuity, matter acknowledging its own persistence. Consciousness in this purely scientific context is the system's capacity to mirror its internal state, and that reflection is inscribed in movement. Even light, the messenger of the cosmos, possesses angular momentum. Photons possess spin 1, which dictates how they polarize and engage with matter. Polarization patterns across the cosmic microwave. background function as the most ancient record of rotational memory in existence. ESA's Planck satellite and NASA's WMAP mission charted these swirls in exquisite detail, revealing faint B-mode patterns, signatures of primordial gravitational waves rippling from the universe's first motion. So when you gaze at starlight, you are literally observing the memory of spin, light twisted and elongated by billions of years of motion. And that light enters your eyes, initiates chemical reactions, and becomes part of your own neural motion. In that manner, the universe does not just remember its spin, it continues to experience it through every observer it generates. Even as the cosmos expands and cools, these traces endure. Galaxies may decelerate, but their angular momentum never vanishes. It is transferred to intergalactic gas, to dark matter halos, to radiation. The JWST has identified faint filaments of gas stretching between ancient galaxies, structures defined by those very transfers of spin. Every wisp of matter still moves to the rhythm established 13.8 billion years ago, and when the last stars dim and motion becomes silence, those patterns encoded in gravitational waves, particle spin, and solidified light will still ripple faintly through unoccupied space. They are not absent. They are inscribed into the configuration of everything that endures. Like fossils of rotation, they constitute the universe's most profound form of memory, motion preserved as geometry. Carl Sagan once mused, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the terminology of physics, that knowing is not mystical. It is through motion, energy, and spin. The universe continuously encodes and retrieves its own chronicle. Take a breath, slowly. Every atom inside you continues to revolve, the same spin that once ignited the first stars. You are a moving archive, a living part of the universe's ongoing memory. And as we trace that concept, that motion may be the cosmos recollecting itself. A new horizon materializes. Because if memory is movement, then perhaps what we call life is the brief instant when the universe decelerates just sufficiently to perceive it's still spinning. That, dear listener, is where our next chapter quietly commences. If this quiet odyssey has provided you even a brief moment of tranquility, I am deeply humbled you have spent it here with me. A simple like or a soft tap on subscribe signifies more than you can comprehend. It is what permits me to keep creating these cosmic lullabies for wandering minds like yours. And if you are feeling generous, please share in the comments where you are tonight and what time it is where you are listening. I cherish seeing how far these quiet expeditions drift across the globe, from one sleepy corner of the planet to another. Your words, your presence, even your stillness. They are like minuscule stars guiding me onward, and I treasure them profoundly. Until next time, may the universe revolve softly around you.